Hello everyone. Um, Continuing on the series of videos on digital system design, today we are going to look a bit further beyond what we have done so far towards the direction of systems on chip. So let's start by sort of understanding what is the need for a system on chip, or what motivates the drive towards system on chip, and look a little bit at what the architecture of a typical system on chip is like. So to understand the background of why modern digital design sort of goes towards this idea of systems on chip, and this is basically the reason why we are looking at it as part of this course, right? It's the natural sort of end game as far as digital design is concerned, at least as things stand right now, right? And what I mean by that is, we started off with a notion of how we could integrate systems, more and more transistors on the same chip, right? And somewhere along the way, people also observed that as long as the transistors are on the same chip, they can communicate more easily than if you need to go off the chip and onto another chip. Now this is just due to physical reasons, literally, right? You need larger wires, and therefore you have higher capacitances and higher load when you are trying to go out of one chip and onto another chip. Whereas if you can integrate everything onto the same chip, the wires that you need are smaller, less capacitance, they can be switched faster, and therefore the overall system works better. Now what we saw during the course of this, during the progress of this course on digital system design, is that we basically built up this notion of how we can do hierarchical design, right? We started off with simple components, gates. From there we went to modules like adders, multipliers, to subsystems like ALUs, decoders, and so on, and then finally to entire almost systems, right, large components like a CPU. The next stage beyond that is basically what would be called a system on chip. Now we have already seen a little bit about what a system on chip looks like, in the sense that you have a CPU and you have peripherals associated with it. So many of the concepts that we'll be talking about now are already sort of touched upon in various parts. What we'll be looking at is a more systematic approach to sort of understand what is happening here. Now, in order to really appreciate why this has happened, there is this concept called Moore's law, which was basically sort of observation by Gordon Moore, who was one of the founders of Intel, right? And this was done way back in 1965, where he essentially sort of looked at how transistor densities, or the number of transistors that could be integrated on a given silicon surface, was increasing over time, right? And the reason it was increasing, of course, was that technology was getting better. People had better understanding of how to make smaller and smaller transistors and fit more of them in a given surface area. And as that progressed, it seemed as though that would continue growing exponentially, right? And Moore's law basically sort of extrapolated from there and said that, this kind of exponential growth should continue for a while, and therefore you should see that the number of transistors that you can put within a given silicon surface is likely to grow exponentially, which meant that within a few decades, right, 2-3 decades, you would be talking about millions of transistors on a chip. And that has actually continued all the way until now, where we are actually hitting the point of something like 100 billion transistors on a single chip, right? Now those are ridiculously large numbers of transistors if you think about it, right? And of course the point is that you have the capability to put so many transistors. The question then becomes, what do you do with them, right? If you just say, okay, I'm going to put more adders, more multipliers, that doesn't really help beyond a point, because what you need is some place to store the data. So then maybe you can say, okay, I'll use it for storing more data. And ultimately that is sort of what happens in modern SoCs, where a large part of the chip surface is basically used for storing information, either as cache memory or some other kind of structure that's used for storage. But at the same time, you have these transistors, and therefore you can try integrating more and more functionality onto a single chip. The bottom line is, why would we want to do this? It's because that leads to a lower system level cost, right? If you can have multiple functionalities integrated on a single chip, that means that your bill of materials, the number of parts that you need to buy in order to actually build a system, reduces, and therefore the complexity of the design, the number of places where it can fail, the number of ways in which it can fail, all kind of reduce. Now, of course, this integration density applies both to analog and digital design. On the other hand, analog design typically tends to favor systems where you have the need for very good matching between transistors, which typically means that you are no longer working with the smallest possible transistors. You need transistors of a certain size in order to guarantee certain kinds of matching behavior. In other words, how the different transistors look to each other, right? Are they sort of similar? Yes, on paper we would like them to be similar, but when you actually construct them, to say that two transistors behave in a similar manner, you need to have both of them to be at least of some minimum size. On the other hand, digital design is just switching. It's either on or off, 0 or 1, and therefore the exact sort of fidelity between transistors matters much less than in analog circuits, which is why digital designs tend to go for the smallest possible transistors, correspondingly the largest numbers of transistors integrated on a given piece of silicon. Okay. So that ultimately is this term very large scale integration. The people who originally came up with that definition of very large scale integration, given that that was more than 40 years ago, would probably be absolutely shocked by what the number of transistors on a chip today is, right? Because at that point, even something like a few thousand transistors on a chip would be considered very large scale, right? And now we are literally talking about a billion plus transistors on a chip. But the point stands, what matters is how do you make use of these transistors, and that's basically where this entire sort of progression through digital design, where we have gone to higher and higher levels of abstraction, finally now getting to the point where we are going to discuss a system on chip. Historically, in the 80s and 90s, right, you had, well, in the 80s primarily people were still sort of defining CPUs. So there were new kinds of CPUs that were being built. So there wasn't really a notion of having an entire system integrated into a single chip, right? A CPU played its part. In fact, you might even have a scenario where you might have a custom ALU and the decoder and the instruction memory all put together separately, and literally the CPU being assembled on a board. Now by the 80s that was no longer the case. You had already Intel was coming out with its processors, the 8086 family, and there were others. There was Motorola, and there were a few other chip manufacturers as well who had full-blown CPUs. But the notion of integrating a CPU along with some basic peripherals, let's say the UART or an SPI communication interface, or some kind of maybe a parallel port or something of that sort which would allow communication between such chips, started becoming more common in the 90s. By the year, or rather in the 2000s, right, much more complex SoCs, the system on chip concept had sort of come into play at that point, right. They would actually tend to have multiple processors and also specialized hardware, for example image processing hardware that would allow you to display or maybe speed up the rate at which JPEG could be decoded for display on a screen. In the 2010s, we started seeing heterogeneous computing, and what that means is, for example, you might have graphic processing units that are capable of performing certain kinds of mathematical operations much more efficiently than CPUs. You might have also various other kinds of things like certain specific hardware accelerators, in particular for cryptography applications, right, or possibly for some kind of compression, primarily around image processing, because for a long time that was the most compute intensive application that people were looking at, right, but various kinds of signal processing systems. By the late 2010s, AI had started becoming a major requirement, right, which meant that the basic neural networks, how do we accelerate them, started coming into the picture. And nowadays, of course, we are actually having to move to highly customized architectures, right, where of course currently the primary driving factor is AI or AI ML, but we are increasingly looking at domain specific systems on chip, right. So we talk about mobile SoCs or laptop MPUs or APUs, application programming units, right. And there are various kinds of things that sort of lead to specialization. Not just that, there are certain kinds of processors that are sort of specialized for automotive applications, others for mission critical applications, others for extremely high compute, right. And the idea is that you try and take the right kind of SoC that solves the problem you have. Okay. And needless to say, each of these is sort of increasing in size as time goes on. So what exactly is the system on chip? Essentially, we integrate as many or all if possible all the components of a computer or electronic system onto a single chip, right. So, this notion of integrating on a single chip is what designs a system on chip. The one thing which actually is happening today is perhaps it's not entirely accurate to call all of today's system on chip. They are probably more accurately called a system in package, right. What that means is that you typically have what looks like a chip, but it's not one single silicon wafer, or rather a single silicon die, right. The die, by the way, is the specific unit of the silicon wafer that is cut out and actually has all the circuitry that you need. So, modern systems typically tend to be system in package, which means that you have a package with appropriate input output pins, but which may contain separate pieces of silicon that are all integrated together on some kind of a common substrate, right. It differs a little bit from a system on chip, but it also shares a lot of similarities. So, for practical purposes, right now we are not really going to differentiate between them. Now, what are the market drivers for this kind of system on chip integration? Mobile computing, IoT applications, pretty much everything in embedded systems, automotive, right, and cloud computing, interestingly, because although cloud computing primarily revolves around the idea of compute, there are scenarios where you might want to do, for example, high speed cryptography, right, or various other kinds of processing that require you to have a system on chip with that kind of functionality baked into it. Now, the market would like to have such chips that can have a large amount of functionality, but then comes the question, what enables that technology? And that's where the technology comes in, right. The technology advances. Advanced process nodes, you keep hearing about things like, of course, 180 nanometer is considered old at this point, right. It's no longer used for the latest processes, although it is still commonly used for slightly older and more sort of applications that do not require extremely high performance, but do require things like robustness against supply voltage fluctuations and things of that sort, right. But advanced process nodes now go down to all the way to the point where you're talking about 5 nanometer, 3 nanometer, and possibly even sub 2 nanometer feature sizes. So, what that means is the size of the transistors that is being built is on the nanometer scale, right, and that also correspondingly means that it is at a point where it's very difficult to really control how accurately these transistors are being designed and printed onto the wafer, which means that the kind of design techniques that need to be applied over here are very different than what it would be in slightly older technologies, or at least at the process level they are different. It also means that you need to have extensive software support, including IP reuse, design automation tools. EDA is electronic design automation, and without EDA you cannot really design large modern systems. And of course, you need to have some kind of standardized interfaces so that different groups of people could design different components of a system and still have them integrated together. So, the core components of any system on chip would typically be in several categories. They would have processing elements, which would include general purpose CPUs, real time processors for real time tasks, right. So, for example, if you have deadlines that need to be met, there are processors with extra support for certain kinds of interrupts and certain kinds of real time behavior. Digital signal processors, GPUs, NPUs are various kinds of processors that are sort of tuned to specific application domains. They perform extremely well in those domains, but may not be well suited to run an operating system, for example. You also have memory subsystems, right. So, you have the on-chip SRAM, which is used for storage. You also tend to have various cache hierarchies, right. And of course, you also want to talk to external DRAM, because the largest volume of memory is in external memory. Now, in order to have these are the sort of main, the compute and storage, you also need communication, which allows you to actually communicate, or rather get data from the memory into the processing and vice versa, right. And this itself becomes a fairly complicated segment of the overall system that you are trying to build. And of course, you finally need to talk to the outside world, which means you need I/O and peripherals of various kinds, including USB, Ethernet, PCI Express for integrating with high-speed peripherals and so on. Nowadays, especially, there are a large number of custom accelerators that need to be integrated into a chip, as also you need to have various kinds of analog or mixed signal blocks, because increasingly the tendency is to move towards trying to integrate even the analog components, for example the analog to digital converters as part of let's say a microphone or a camera, or maybe something else which can actually generate a driver signal for an LED display. All of those are mixed signal components, or maybe the modem which actually does the radio frequency signal generation for communication. All of these also we try to integrate within the same system. Now, there are many common processor families which you are likely to encounter at some point, right, as you go through and come across this thing. Interestingly enough, the traditional desktop processors, Intel and AMD, do not sort of tend to come up very high in this list because they are not really designed as systems on chip. Having said that, the newer processors, for example, the APUs that come from AMD, do have a lot of features that resemble SoCs, and the sort of trend is to move towards trying to integrate more components onto the same chip, right. On the other hand, a company like ARM almost from the beginning was focused on the idea of building systems, and they have the ARM Cortex family, which is, they essentially chose three names, right. The A series is high performance application processors, the R series is for real time, and M is the low end microcontrollers. Of course, obviously they chose the name because it stands for ARM, but that's not the origin of the name ARM itself. That stood for advanced RISC machines. So why do they have these three different families? As you can imagine, they have different characteristics. Something which is extremely good at processing general purpose applications may not be particularly low power enough for a general microcontroller application, or may not have certain kinds of interfaces that a microcontroller application or an embedded application might need. So you have different families, each of which specializes in different areas. Of late, of course, we have had a lot of growth in the RISC-V ecosystem, right. It's an open source ISA, instruction set architecture, which is customizable, and lot of companies as well as research groups have basically looked at extending the RISC-V ISA for various purposes. It's seeing a lot of increasing commercial adoption recently, but at the end of the day, I mean, at least as of now, it is not yet at a point where it is a full-blown challenger to something like ARM. It is definitely, it could get there though in the near future. So it's definitely the most promising candidate in terms of what is likely to be coming up next if something is to displace ARM. Now, having said that, you also have a lot of other kinds of more custom systems on chip. There is the so-called big dot little architecture, which is also usually done with ARM cores, right? And many phones nowadays especially, you might see that they have what are called performance versus efficiency cores, and this is making its way even into things like laptop processors and so on. The idea is that certain cores, certain processing cores can be tuned to have extremely high performance. What that means is that you have like very deep levels of pipelining, advanced sort of instruction prediction and speculative execution, all those kinds of features, right? But they do consume more power. On the other hand, there could be others that are more efficient in the sense that they have much less power consumption, but they may also not do as well in terms of raw computational power. So having a mix of such cores where you have maybe 4 performance cores and 4 efficiency cores, and then the operating system can decide which process goes where, is something that gives you a lot of flexibility in terms of how to operate. There are systems like, for example, the Apple M series processors, which very tightly integrate the CPU as well as the GPU cores, right. Both of them get access to the same memory, and that basically has a very significant impact on how efficiently computation can happen. And of course, increasingly we are seeing domain specific processors, the NPUs, neural processing units, and various other kinds of accelerators that are being baked into various applications. So a word about the memory hierarchy. This is something that we have looked at earlier, right. Typically a processor core has registers inside it. It also has, in some cases, you might have something called a scratchpad memory or some kind of tightly coupled memory. These are typically what are known as the on-chip memory blocks, right. They are typically SRAM, static RAM, and they tend to be extremely fast, right? Almost to the point where you have something like registers, right? Maybe not quite as fast, but you can also, especially in the case of a scratch pad memory, it's possible to actually explicitly control how you use it. Now, a scratch pad memory is very similar to what's called the level 1 cache memory. The primary difference being that the cache memory is sort of used for a slightly different purpose. What happens in cache is, you can see this pyramid of memory structures that I have drawn over here. The idea over here is that the main memory, right, which is typically external DRAM, dynamic RAM, which could be large, it could be in the several gigabytes range, tends to be, well, hundreds to thousands of cycles. It could be even, so 300 is just a number that I have put over here, it could be like easily thousands of cycles as well. What that means is, let's say that you try to load from DRAM, your processor is then going to wait for the next 1000 cycles before it gets any data. It cannot do anything in the meantime. Of course, modern systems typically tend to sort of have some other ways by which they can switch over to another application or to do something else during the meantime, but in general this is a very real problem. Now, what happens is, because of this notion of what's called the locality of reference, which means that you can also, if you access one memory location, there's a good probability that you will also access memory locations close to that. People came up with the idea of caching memory, and what that means is, I will use, let's say, a level 1 cache, which could be pretty small, it's only a few kilobytes in size, but if I access one particular element from main memory, rather than just reading, let's say, one word of data, what I do is I read in one entire set of maybe 8 to 16 words and put them into the level 1 cache. The idea being that if I actually accessed one word, then maybe I would also access the next second and third and fourth words as well. It also turns out that DRAM, even though it takes a lot of time for accessing one memory location, has a high throughput, which means that after that first element is accessed, the next several elements are going to come at very high speed, which means that I can easily fill up my cache lines by accessing consecutive memory locations from DRAM. And by having the data in L1 cache, I can literally access it within 1 to 3 clock cycles. It's almost like a register itself, right? So I literally ask for memory, ask for data from memory or write to memory, and the instruction basically executes in a single cycle. Now, scratch pad memory is very similar to L1 cache, except that the programmer gets direct control over what to put in scratch pad memory and what to remove from scratch pad memory, whereas caches are usually automatically handled by hardware. Now, why do we have these different levels out here? Because we would like to have another L2 cache which is of larger size, but the moment you go for larger sizes, let's say a megabyte or so, it turns out you can no longer access it in 1 or 2 clock cycles, you probably need around 10 to 20 clock cycles. Similarly, if you want to go for several megabytes, it increases still further. So, we tend to generally have a hierarchy of such cache memories that are present in any system on chip. Okay. And of course, right at the bottom of this hierarchy is the off-chip, or rather the non-volatile storage, right, which tends to be things like flash drives or SSDs and so on, which are very large capacity. You can have terabytes of storage, but you can actually incur times of millions of clock cycles, right, in order to access data from one of these. Now, it's actually worth sort of taking a moment to think about that, right? The reason why this happens is because our main processor is working at clocks that are more than 1 gigahertz in speed, right, which means that a million clock cycles on that processor is only 1 millisecond of real time. So, 1 millisecond is still fairly fast from a human being's point of view, and therefore these storage systems do appear to be fast for us as users, but for a CPU it literally takes a million clock cycles to access, right. So, because of that, we have this hierarchy of memory that is needed in order to get a certain degree of performance. So, with all of that in mind, memory also needs to be organized, and the system on chip needs to have various structures, including memory controllers, right, various kinds of DDR interfaces and so on, which are used to communicate with these different external components. But hardware alone cannot solve the entire problem. This is where we increasingly come to the interface between hardware and software, and it turns out that we need to bring in concepts like virtual memory and memory protection, in which have a very strong interplay with how we write software and how we actually write applications that run on these systems, right? And without understanding the software components, it becomes hard to design the hardware. Similarly, without understanding what the hardware is capable of, it's impossible to write good software as well, right? So we have now got to the point where we need some degree of abstraction which takes us into the software domain, but we also need to understand what the underlying processor is capable of. This also leads to a number of different optimization techniques which might end up happening either in hardware or in software, right? Prefetching strategies, how do we allocate the memory bandwidth for various operations and so on, which ultimately turn out to have a very significant impact on the kind of performance that you can extract from a system.